With that, we will completely shift our meeting over to Borja's control. He has his slides going, and as I mentioned, Borja is with flight level engineering, and he has been updating this report on a regular basis. They've been doing it. He can talk to you about the contract and so forth. But it's certainly stuff that I've been working with since I joined the eVTOL world. And these guys are way ahead of where a lot of us already are. So it's very much worthwhile for us to listen from the masters. So at this point, I'll hand it over to you, Borja, and off you go.
All right, thank you so much, Al. I appreciate the introduction. I wanted to, this is going to be a little bit of a collaborative effort between Noel Dirksen and I. We've been working together for the last several years. Noel has been working on these kinds of projects for much longer than that. So it'll be a team effort today in the presentation. I'll have a portion of the slides. Noel will also present a couple of the slides. We'll kind of go back and forth. And Noel will be kind of spearheading the questions and answers today. Noel is an independent aerospace consultant. He is working with us in this project, so it'll be both of us today. We wanted to go ahead and kind of start a little bit and basically just say, I guess, thank you for our NASA sponsors. I don't know if Star Jin is on the line today or Ken Goodrich, but this is a NASA-led and funded project, and it's in collaboration with the FAA. And it really, that's a very important part because none of the certification requirements that we're proposing really make any sense unless they make sense to the FAA. So NASA is funding this through the Office of Advanced Air Mobility for the development of certification paths for SVO, UAM, and AAM. Now, if you've heard any of our previous presentations, we usually say that these proposals are solidly set in Jello. We have updated the graphic, and now we think that we are set in sand. A little bit firmer, but no doubt still pretty shifty. We would definitely like your input. Okay, so first of all, we kind of need to recognize where we are and where we're going. In this slide, we currently have some tension going on. We're looking at two different characters here. We've got Roger Ramjet on the left, who's been flying airplanes for decades and certifying Roger Ramjet-like aircraft. Then on the right-hand side, we've got the new kid on the block. We've called him affectionately the Nintendo kid. And he's going to be operating, or she's going to be operating, basically a whole new class of aircraft. Now, the Roger Ramjet aircraft, basically, let's see what's going on here with my controls. There we go. The Roger aircraft is mechanical controls or fly-by-wire controls that mimic mechanical controls. There are basically separate propulsion and control systems that are managed basically by Roger. For the Nintendo kid, we're talking about a new set of aircraft that have basically integrated propulsion and controls. It could have multiple motors, rotors, etc. And more often than not, they just can't be managed by a human. There's just too many things to move. In Roger's aircraft, basically it's assumed that the pilot will save the aircraft after the automation fails. In the Nintendo kit aircraft, it has automation that is designed to fail operational. So if the automation fails completely, essentially aircraft crashes. On the Roger Ramjet side, if the pilot messes up, then the aircraft crashes. For the Nintendo kid, the aircraft features are designed so that the basically automation can save the aircraft from pilot errors. Now, one of the things that we looked at was basically in general aviation single pilot operations, the pilot has a failure rate of something worse than 10 to the 5th for loss of control accidents. So on the automation side, we can basically design the automation to whatever we want it to be. It can be boiled down to basically a cost versus functionality relationship. So an interesting implication falls out of this if you think about it. If we want to improve safety, beyond basically what a single pilot can provide, then we have to move past the philosophy that the pilot backs up the automation. Al, one thing that I'm seeing on my screen is that I've got a green box. I'm not sure if it's cutting off the bottom of the slide or not. Is that a problem?
I think we can see everything.
Okay.
Yeah, I can see everything. That's good.
Okay, thank you. Okay, so let's talk a little bit about the aircraft certification process. Historically, after an OEM has developed a new technology, say they go to the FAA to get it certified, and typically that could happen under a special condition. It turns out that, of course, as this process is going on, that the new technology has, well, some operational capability that's new, and that's kind of the purpose. That's why it was designed in the first place. So then the FAA pilot certification side comes in and basically evaluates how this thing operates, how someone will learn how to operate it, and then is tasked with including in pilot licensing. Historically, the effect is that the pilot must learn both the existing manual operation, but also the new automated version of how things work. Now, in the work that we're doing, we would like to literally change this, and this is a key concept that's at the very heart of our project. So instead, what we'd like to do is to turn this process upside down and start with the desired operational capability and the desired pilot interface. That will then determine what the aircraft certification requirements are instead of vice versa. So the effect is that we end up with simplified vehicle operations through standardized automation and the potential to eliminate certain manual tasks. And eliminating manual tasks is a key here in our concepts and proposals. But as you can imagine, the FAA is going to need OEMs to generate operational data in order for any new technology to be able to gain certification credit. And we believe that technology demonstrations are just not going to be enough for the FAA to provide that credit. So this kind of feeds into the existing safety philosophy, if you will. Currently, we have power plants and flight controls, which are governed by design requirements. For example, flight control cables need to be made of stainless steel. However, I guess some of the systems and instrumentation are governed by a different philosophy. And the gist is that we basically determine the severity of the failure, and then that determines the probability of failure. After failure, of course, it's assumed that the pilot will always do the right thing. And so we see that systems are designed basically with the assumption that the pilot is the backup. And system and reliability levels are then currently set based on the number of passengers in the aircraft. So we would also like to be able to change the system so that all systems, including power plants and controls, will be governed by the effect of the failure and the probability of failure, not the design requirements. So this has some interesting implications. One, that the designer is kind of free to come up with new designs that could improve safety, reliability, economics, etc., without being tied to the design requirements themselves. Now, in the past, in the presentation, I mentioned that single pilot operations in GA have a failure rate of something worse than 10 to the fifth for the pilot. So we expect that the pilot's failure rate will also be included in the safety analysis. Now, we recognize that in emergency situations, of course, this pilot error probably gets even higher. So one of the things that we're recommending to mandate is that any single pilot error cannot cause a catastrophic event. And also, importantly here, that after a failure, that no immediate action is required for continued safe flight. Basically, we're proposing to get the pilot's adrenaline level down to a level that the pilot can think safely and logically. We're also recommending that the pilot is not automatically considered as an acceptable backup. And that kind of goes back to the safety analysis by including the pilot's failure rate. So then the reliability levels are set according to the number of people overall involved in the accident, not just the people that are occupying the aircraft. Okay, so kind of the task that we have taken on, if you will, is how can we create a path from basically where we're at here to where we want to go, And where we are here is, well, basically in some of today's aircraft, like Cessna's 182s, Cirruses, etc. And there is what we assume from NASA and the AAM offices and the like is a nearly fully autonomous aircraft operations. So we've created this path defined by a couple of stepping stones, and the overall philosophy is this crawl, walk, run thing that you've seen before. And there's a couple of stepping stones. Stepping stone number one is SVO1, and it's basically targeting current fixed wing pilots. Now, it has unified like flight controls, so it operates like an aircraft in cruise and operates much simpler in hover than a conventional helicopter does. Some other noticeable things, it has a typical glass cockpit, so it looks a lot like an airplane to existing pilots, except that it hovers much easier than a helicopter does. As all of you know, it takes considerable training and effort to learn how to hover a helicopter. The other things that are included in the list are things that are added because they represent heavy training burdens in the pilot training curriculum that we have looked at for both fixed wing and helicopter folks. The second stepping stone is what we have called SVO2. And here the target is a little different. The target is non-pilots. It has even simpler controls. It basically starts out by assuming that this group of people do not have any aircraft experience, but they do have about 1 to 2 weeks to become a pilot. So in other words, the equivalent time and cost of basically going to truck driving school and becoming a truck driver. In SVO2, however, we're not tied by typical airplane controls. It has controls that are identical in all phases of flight, in cruise and in hover. The displays and the controls are all integrated, as are the systems. And as you can see, that there are a lot of automated features. The last stepping stone that we have put in so far is SVO3. And SVO3 is really aimed at the passenger and more of a point and click type of control. The passenger basically designates the destination and has nearly fully autonomous operations. A key point here is that there's basically, in the concept, there's no pilot license requirement. And we'll talk about some of the interesting implications that come out of that in a few slides. Okay, so how do we make this change happen? Well, we can make it happen through the aircraft certification and pilot certification processes, which is basically have been the majority of our involvement in this project. So here's where we're at today. The certification process today is defined by FAR Part 1, which includes all the definitions. This defines airplane, rotorcraft, powered lift, etc. And if you look at the left-hand side of the slide, you can see that the aircraft on the upper left side has airplanes, which are defined by Part 23, rotorcraft under Part 27, and powered lift. These come again straight out of FAR Part 1. Now, a couple of slides ago, we talked about how we generate pilot licenses based on the hardware. Pilot license categories, of course, follow the same path that aircraft certification parts do. So we have airplane, rotorcraft, powered lift, etc. What we're proposing to create is an additional definition, which is SVO. And we define SVO as something that has a safety, automation, and flight characteristics defined in SVO. At the bottom of the slide here, you can see that we've got an expanded version of that definition. It basically says that these are aircraft that meet the requirements of SVO. And in reality, what we're proposing are SVO special conditions for Part 23 aircraft, or SVO special conditions for Part 27 aircraft, etc. Now, interestingly, these machines can be airplanes, they can be rotorcraft, it can be something else. The form of energy that's used, the number of power plants, etc., that really is of immaterial here. The point is that an SVO aircraft SVO is what it behaves like from the pilot's perspective. So if you look at the left side of the slide again, you'll see that we have now added a new aircraft category type for certification, which is called SVO. And it kind of flows down into a new pilot licensing category, which is also SVO with the appropriate ratings. Okay, so something that's kind of came up in a lot of these presentations is how do we manage this certification change while OEMs are currently in the certification process themselves. And well, we have airplanes and rotorcraft obviously that are being certified with the current system, and the current system is stable. But we now have a lot of new designs based on new technology that Nintendo kids have and are creating, and many of these philosophies and design changes could be at a conflict with current regulations or even traditional regulatory philosophies. Fortunately, the FAA has methods to accommodate this, and of course there are special conditions for aircraft design. For example, the GAMA Group, that's the General Aviation Manufacturers Association, has proposed to the FAA that applicants could develop model-specific training for pilot certification requirements with the FAA. Now, the unfortunate effect is that this tends to make the requirements custom for each individual aircraft. So unfortunately, they require much more time to certify and develop than a standard method of certification. So the goal here is to create a standardized way of certifying SVO eVTOL aircraft using new technologies or making new technologies viable and creating a standard path so that when a OEM goes down a standard path instead of having a customized certification each and every time. And just to kind of graphically show how this could work, we basically have a couple of bars in this slide. There's the upper green bar, which kind of shows the current way, and that's the way that most aircraft are certified that way today. The next one is the red bar. The red bar shows that the FAA basically is getting more and more custom certifications with special conditions, things of that nature. And we expect that probably many more certifications will follow that path. As Al mentioned, there are several hundred OEMs working on these types of vehicles. The goal of our project, though, is to develop the blue path. So that's when we create a standardized way of developing SVO and fly-by-wire eVTOL aircraft that doesn't conflict with the folks that are in the current pipeline. So if there's a standardized ways of certifying these machines, the expectation is that as the standardization develops, more and more aircraft will use a standardized method and fewer would use the customized method. Okay, so just to kind of recap this general philosophy, again, here's basically the stepping stone general philosophy. SVO1 leverages current fixed-wing pilots. Now, we want to significantly reduce the burden for VTOL aircraft and improve the reliability of automation so we can eliminate some of these heavy training burdens and certification tasks for pilots. And again, as a reminder, we believe that we need to use data from existing operations with automation to get this type of certification. We believe that this is a UAM, AAM industry enabler. SVO2 again is designed for pilots with no previous experience, where they basically command the flight path. We basically focus there on navigating, not maneuvering, or providing stability. For example, most pre-flight planning is done automatically. This kind of allows UAM, AM industry to rapidly grow by supplying operators to much larger traffic volumes. And finally, SVO3. Now, SVO3 again is the kind of envisioned as the point and click control with fully automated planning and requires ATC or the fleet operator to change the destination or routing. And SVO3 has some very interesting implications because we're suggesting that no pilot license is required. And this is interesting because throughout the FARs, you can see the concept time and time again that the pilot is the ultimate authority for safety and has responsibility for safety as well. Now, if we don't require a pilot's license, then it's not reasonable to expect the pilot to have the responsibility for safety. So safety must be realized somewhere else. And the only real place that makes a lot of sense for that to rest is on the operating organization. So the implication here is that SVO3 really works only as part of a Part 135 or Part 121 operations in a controlled environment. Now that's a big change for FAA certification philosophy. and that the pilot is not the ultimate authority, that someone else is. So now in the next few slides, we'd like to transition a little bit into some of the previous work that we have done that relates specifically some flight test examples. And I'd like to transition over to Noel Dirksen for the next couple of slides.
Thank you, Borja. Good job, by the way. So I'd like to talk a little bit about some of the history of how we got here. Of course, none of this happened just spontaneously. Like everything else in technology and science, it builds on things that have happened in the past. So I would like to start with the upper left picture. That's a picture of a investigator at NASA Langley, Eric Stewart in particular. He did a lot of work in the 80s with NASA simulation and developed a flight control concept that he called Easy Fly. And the Easy Fly concept basically said that the pilots aren't really interested in controlling the position of the elevator, the position of the ailerons, etc. What they really are interested in is developing or controlling the direction of the flight path and including the magnitude of the flight path, basically a flight path vector command system. So that's what he developed in the simulation. And he found some really interesting results. Basically what he found was that non-pilots were capable of flying an instrument pattern and an ILS to about the ATP level of performance with very little or no training. So back in the 90s then, late 90s, I was fortunate enough to be working at Beech Aircraft Company and working with NASA, and we developed the Agate program. Actually, NASA developed the Agate program, and I was fortunate enough to be involved with it. That's what the Bonanza in the middle is all about. So we put the flight control system that Eric Stewart had envisioned in the simulator, and we put it in a flying aircraft, that Bonanza. And we had some very interesting results with that. We also did automated landing with it and things like that, because those are some things we found doing the flight testing of that Easy Fly control system that were required for pilots with very little or no training. The lower right picture is a picture of an Avion with the company that Borja owns and operates, and he'll talk more about that later. Next slide, please. So this is an interesting story that comes out of the Bonanza. And Borja will talk about some interesting stories that come out of the Navion in a little bit. But the Bonanza had the Easy Fly control system. And as I mentioned, it controls the flight path vector. It also had envelope protections, so you couldn't stall the airplane. You could not overbank it. You could not over-G it. You could not run it into the ground. So one of the things that the president of Beech Aircraft wanted to do is he wanted me to take him on a test flight to demonstrate this new technology that we were developing with NASA. So I agreed to do that, but then I thought it might be a good idea to have a practice run before I flew with the president of my company. So I walked into our office area and I generally announced this, I need to do a practice demonstration. The requirements for the practice demonstratee are that you don't know how to fly an airplane, but you're comfortable flying one. A young lady raised her hand. She was our tech writer. She had never flown an airplane before, but she had flown in small airplanes. So I said, you'll do, let's go. So we walked out to the ramp and I gave her a short briefing on how to open the door, things like that, put her in the left side of the airplane, the pilot side, where the fly-by-wire control system is. And I emphasized that you cannot hurt this airplane. And once we get off the ground, you are going to be flying it. So that's exactly what we did. We took off. I gave her a short briefing of what the stick does. If you move the stick back, the airplane goes up. If you move the stick left, it turns left, etc. Now, there's a speed command lever. So you're just commanding the speed to fly. I'll tell you the speeds to fly. And so we started flying, and she started flying the airplane around and said, yank hard, bank hard, push, pull, do what you want. You can't hurt this airplane. You can't hurt us. You can't hurt the airplane. So after about 5 minutes, she got pretty bold, and she was doing 60-degree bank turns with the airplane holding altitude within 50 feet and airspeed within 5 knots, just like a ATP pilot would. And so after about 15-20 minutes of doing this VFR, just yanking and banking, I said, let's put this hood on, an IFR hood. So now after 15 minutes of flight instruction, she's flying under instrument conditions, and the instrument panel looked like the picture on the right. It had a synthetic vision system on the left, and it had a moving map on the right. And then, of course, the safety pod area where I sat with all the round dials and stuff. So now she's flying with a hood on, and we do that for about 10 minutes. And I told her, I'd like you to do the VOR Bravo approach into Beach Field. The VOR Bravo approach is a circling approach with the final approach course 90 degrees to the runway. And the minimum descent altitude is 400 feet above the ground. I told her I wanted her to do it at 140 knots, which is quite fast for a Bonanza, but let's just do it. So I told her to fly to the magenta line, which many of you are familiar with, and I told her the altitude to fly. So she did that. She self-vectored herself onto the approach. Now, this is a young lady that has had less than an hour of flight experience and less than half hour of instrument instruction. She vectors herself onto the final approach course. And once she's on the final approach course, I directed her to go down to the minimum descent altitude, which she did. Now we're going at 140 knots, heading towards the runway, which is 90 degrees from our current path. I told her that when we get about a mile from the runway, I want her to look up, turn right to enter a path parallel to the runway, and we'll set up for a landing. So we get to about a mile away from the runway, doing 140 knots, and I told her to look up, and when she sees the runway, to turn right to parallel the runway. So she looked up from under the hood, and we're going 140 knots, and she's not doing anything. But then she looked at me and she said, "What does the runway look like from the air?" I hadn't thought to tell her what a runway looks like or show her what. So I said, "Turn right hard now." Because on the other side of the runway was airspace controlled by McConnell Air Force Base, and we were not allowed to go there. So at 140 knots, 400 feet above the ground, she slams the stick to the right side of the wall, and the airplane rolls up into a 60-degree bank, holds 400 feet plus or minus 50 feet, and 140 knots plus or minus 5 knots. And now I said, "You can level off now." And she lets go of the stick pops back to the center, and we are parallel to the runway, 140 knots, 400 feet above the ground. And said, "Now you can slow down to 90 knots. So, okay. So she's moved the airspeed command lever from 140 to 90. The airplane slowed down, we put the landing gear down, and we landed. So that's some of the things that we found that were really pretty impressive about this kind of a control system. And we thought it would be good to expand that and move it to VTOL as well. But we'll talk about that a little bit later. Next slide, and I think it's now your turn again, Borja.
Great, thanks, Noel. A couple of additional stories. We were able to take that software architecture and implement it with improvements in our variable stability Navion. It's a 5 degree of freedom in-flight simulator. A couple of short stories here is one, the FAA was gracious enough to allow us to fly with one of its young engineers. And this particular individual had basically no flying experience whatsoever. He was a civil engineer, but was very apprehensive to go flying with us at first. You can kind of see on the left side, you can see I'm getting into the aircraft and Noel is in the back, kind of scratching his chin, figuring out how this flight's going to go. And it actually progressed very well. Little by little, this gentleman felt more and more confident with the aircraft. He really started believing that he wasn't going to hurt the aircraft and that it wasn't going to hurt him as we proceeded to do climbs, descents, turns, fast, slow, etc. This was a very interesting flight because at the end of the flight, about 45 minutes in, I asked them to do a steep turn. And Noel and I are both flight instructors, and it takes some effort to train folks to do a steep turn to within practical test standards. Of course, he didn't know what a steep turn meant, so I said, basically, could you please move the stick to the right and go around 360 degrees and to the left? And he proceeded to do a 50-degree steep turn right and left within PTS standards without any training whatsoever. So that was a pretty remarkable flight that we had. The next example is with the 17-year-old Nintendo kid. Now, this particular example is very meaningful to me because that is my brother-in-law, and he has told me that I could share his story. He had absolutely no aviation experience whatsoever, but he did have lots and lots of video game experience. In fact, we counted, and from the time that he started playing video games when he was 11 till at that time, we counted over 4,500 hours of video game experience, mostly first-person shooters, no aviation-related games. And he too was very apprehensive about going to go flying. Did not have a ground school, did not give him any flight training, but we did go up in the National Aerospace System, and I handed over the flight controls. Again, try to convince him little by little that the aircraft was not going to hurt him, and he was not going to hurt the aircraft. And he was able to basically explore the aircraft and do so with confidence, be able to, again, climbs, descents, steep turns, slow down, increase speed, try to dive the aircraft, felt completely confident, and did a very, very nice job of doing so, again, without any previous experience. So these were a couple of demonstrations. We did many, many more throughout the flight test work that the FAA sponsored us. That work, of course, its main purpose was in part these demonstrations, but more importantly, to be able to generate means and methods of compliance. And so in the next couple of slides, I'd like to talk about that a little bit. What are some of the key takeaways that we picked up from this research? Well, it basically showed us several important things. And one was that a new display concept was required to go along with the flight control system, and that they needed to be developed together and not independently. Once we came across that little nugget, then we realized that as the displays were also developed, we needed to be able to navigate, create a navigation system that was also integrated with the displays and controls, because in reality, all three things affected one another. So a change of the controls affected the displays and affected the navigation, vice versa. And they really couldn't be developed as independent boxes. They really all affected one another. And this kind of came out of this research program. The Easy Fly system accumulated a little over 100 flight hours in a variety of experiments with a variety of individuals. And some of the key takeaways, again, were not necessarily these demonstrations, but some of these means and methods of compliance that we'll talk about in just a moment. I think, Al, how much time do we have for this presentation?
We can go at least till noon, and but typically we'll go a little bit past that when there's interest, if people can hang on. So
Okay.
Go for it.
Well, I've got a video here, but it's 7 minutes long. Maybe I could share this video after the fact if we have enough time. But
well, there you go. We can do that at the end. That'd be great.
Yeah, we'll try to go through these slides, and then if time remains, we'll show you a demonstration of the system. But it is, again, about 7 minutes long. So I'll skip this for now, and let me turn the time over again to Noel Dirksen.
Thank you, Borja. So again, a bit of history is appropriate. That this is really a progression of what has been happening for decades. The fly-by-wire control systems have been mimicking mechanical control systems, as been shown by the V-22 on the left. It's basically, it flies like an airplane when it's in airplane mode, and it flies like a helicopter in helicopter mode. And it's got some transition things that happen in between, but basically it's a helicopter flying like a helicopter, and it's an airplane flying like an airplane. And the control system from the pilot's point of view is an airplane control system or a helicopter control system. So the next thing that ended up happening is the Harrier, of course, has the same kind of control concept, but the Air Force and the Navy decided that that kind of a control concept was just too difficult. The Harrier concept provided a huge training burden, and there were safety implications that were that the military wasn't happy with related to the Harrier, particularly the hovering characteristics of the Harrier. So for the F-35, they developed a new control concept that they called Unified. The Unified system is designed to be operated by fighter pilots, ground attack pilots, basically highly experienced airplane pilots, but pilots who don't spend a lot of time hovering because it's only a takeoff and landing kind of hovering mission. So they created very simplified vertical controls for the V-35. And so we have an airplane that flies like an airplane, but it doesn't fly like a helicopter and hover. It's much simpler, which is very much like the SVO1 concept that we talked about. In fact, that's where we got it, is to make it very F-35-like. So the next thing that we decided we needed to do was to create the simplified flight control concept and take it to airplanes as well for pilots who currently don't exist as pilots yet. So Easy Fly system, the vertical version. Now we've heard a lot about the Easy Fly airplane system, which is what we talked about with the Navion and the Bonanza. But we've been developing the vertical version of Easy Fly as well. And we'll talk about that on the next slide. But that is, the purpose of this whole concept is to create a very easy to fly aircraft, and an aircraft that is very tolerant to pilot errors, and in fact, for most cases, prevents pilot errors from causing accidents. Next slide, please. So basically we have the SVO concept, which has simplified flight controls for hover, but airplane controls for going fast. And what you'll see is that on the right side, there are a bunch of bars. Each bar represents an axis of the aircraft. The color of the bar represents how the aircraft is controlled. Like for instance, the second bar down is the bank control inceptor. So on the far left side, at slow speed, the left side of the chart, you'll see that the unified control system, the inceptor is a bank command system. On the right side, it fades back to airplane mode, where the right inceptor is a roll rate command, like an airplane. And another example of that is, say, the bottom bar. The green bar, the pedals control yaw rate, and the right side controls side slip. So if the control systems fade back and forth based on speed. Next, Bora, please. SVO2 is intended to simplify the entire flight envelope so that it's consistent across the whole speed range. And what you see is all green bars, which basically does is it remaps the control inceptor to aircraft motion so that it is consistent across the entire speed range, so that a control motion in hover results in the same control motion for airplane mode. For the airplane response in airplane mode. So we end up with some scaling differences, but basically the aircraft behaves the same at 0 speed, 1 knot, 5 knots, 10, 15, 30, 50, 100, 150. It's basically the same input to output mapping, independent of speed. Next, Borhan, I think it's your turn again.
Thanks, Noel.
Borhan, are you there? You may be muted.
Oh, sorry, I apologize. Okay, so one of the things that came out of this FAA-funded flight test work was not just these demonstrations, but the need basically for new means and methods of compliance, because some of these revolutionary characteristics of an SVO2-like system, for example, one, there is no attitude indicator. So the flight controls take care of attitude. Now, there's no flight director to show what attitude to fly because there's no attitude indicator. So the airplane basically is following a flight path marker or the flight plan the pilot again does not control attitude like in a classical aircraft. There is no trend indication of airspeed or altitude in the displays because the control system basically takes care of altitude and airspeed management. Also, there's a digital airspeed and altitude of displays just because ATC sometimes asks you what speed or what altitude you're at. Another interesting thing that kind of fell out of this is the pilot cannot go slower than the approach speed with less than full power when the lift fans are not engaged. At full power, the airplane will slow to no less than maximum glide speed. If you think about it, one of the things that this kind of implies is that there's no stall speed, and the implications there on aircraft certification and airman certification. Also, there are basically no lateral or vertical deviation indicators in the SVO2 concept with EasyFly. So the reason for that, of course, is that the flight controls basically follow the desired track. Another interesting thing that came out is that there isn't the traditional autopilot mode control or mode enunciation panel because there's no autopilot. The pilot does not select the modes. And also, there is no mechanical backup or direct mode. The system assumes to have a reliability level sufficient for it to be always on. So just to kind of summarize some of these concepts that we've talked about today, and basically the fallout of this work was that it became an opportunity to be able to generate new means and methods of compliance because of the basically improvements in low-cost electronics, the capabilities of fly-by-wire, the desire to reduce pilot error accidents, and of course the desire to reduce training costs. And the work that was again funded by the FAA started this process, provided actionable data and work that has been, I believe, will be publicly available very soon. Okay, so we want to kind of go back out of the flight test phase and kind of finish off with these NASA funded work that we talked about initially. So we'll go back to that presentation, and we basically want to be able to summarize a certification path, if you will. So first of all, we kind of go back to recognizing where we are again today. We have to recognize that we're not going to get another rewrite of Part 23 in the foreseeable future. We've already had that fairly recently, and the special conditions that we currently have are unique to basically every eVTOL and SVO design. So that requires individual model-specific training for each new design. What we want, we would like to create this proposed certification path. Step one along that is to create a generic set of special conditions by collecting many of the conditions that are being applied today to eVTOLs and SVO, or that are being proposed, and collect those together. This will basically create a standard by which companies can expect to bring the certification instead of having to negotiate from scratch for basically each new design. We also expect to create a minimum set of automated functions that could be lumped together in an SVO1 or 2 or 3 package, and propose that set of standardized packages, automation, to affect the pilot knowledge skills required for licensing. So the effect then could be that the current airman certifications can be used, with the result being a normal license with restrictions to limit operations to SVO with certain packages, kind of like the centerline thrust restriction that is used today for multi-engine ratings. So additionally, we want to convert those generic special conditions in the future to a new part and to create a license from those special standardized features, which can create an airman certification standard for SVO1 and SVO2. But because of the federal effort that would be required to create a new part, it is much more likely that these would be lumped together into a set of proposed SVO special conditions for Part 23 aircraft or Part 27, etc. Now, just to kind of close this out here, we have basically one more slide to go. Is that we report to our sponsor NASA and to the FAA and our industry advisory team basically every quarter. And I would like to basically briefly just like to go through some of the changes that we've made since our last report. That last report a few months ago was about 80 pages long. We're now all over 200 pages. We've created a complete draft for a new proposed Part 53 with SVO1 and SVO2 special conditions for Part 23. We've also created a separate set of reliability requirements, which pulls in the concept that power plants and controls are governed by probability and a failure and the effect of the failure as opposed to design requirements like we talked about before. We've also created two sets of reliability requirements, one for commercial operations over densely populated areas, and the other, which is basically what we have today. The densely populated areas are patterned closely after Category A of Part 27 and Part 29 that Europe uses today. We've also started a proposed advisory circular to provide a means of compliance that we have developed on the aircraft, on the airman certification side. We've acknowledged the industry proposals by Gamma and others to the FAA for specific model training in the short term. We've also proposed additions to Part 61 for SVO1 and SVO2 for all the pilot types that are listed in Part 61. And lastly, we have started looking at operational rules. Some of these examples, for example, Part 91-205, which lists the instrumentation requirement for fire flight. That doesn't make a lot of sense for some of these things, especially when you look at SVO2, where the flight controls provide attitude. So Part 91-205 assumes the pilot will manually stabilize the aircraft. That's automatically taken care of. So the display of attitude is really not required. So we've looked at those kinds of things and expect basically many more changes to follow. So with that, we'd like to go ahead and wrap up the presentation. And I'll turn the time over to Noel, and we'd like to open it up for questions and answers if we have a few minutes left, Al.
Yeah, we do.
You're going to give me the rotten tomatoes.
Oh, sorry, hold on. There they come. Got them.
Thanks.
You said rotten tomatoes. I figured we'd throw some.
Go ahead. Ready for questions.
I'll go ahead and start it up. I'll warm up. So the unified theory that you presented sounds great, and the easy fly sounds great. But what you had shown us there was that SVO1 will use one and with one kind of inceptor mechanization, and then you switch hands and so forth for SVO2. Why both? Why not pick a winner and just go with one?
So the reason for that is that we believe that in order to get to the end state, which is what NASA defines as a nearly or fully autonomous aircraft, that we need to create a path to get there. So we have created stepping stones that define that path. So where we are today is the jumping off point, which is conventional airplanes and conventional helicopters with conventional FMSs and conventional cockpit instrumentation. So stepping stone one is a unified control system. And we felt that it would be best to start with the unified control system because there's already a existing population of pilots, especially in the UAM world. The UAM operators, or the people who want to be UAM operators, seem to think that they will tap into the existing pool of commercial pilots to be the operators of their aircraft to start with. So because of that, we felt it was appropriate to leverage the existing pool of commercial pilots who know how to fly airplanes. So one of the things that we've done is we looked at the population of pilots and the trend in population of pilots. One of the things that we found is the population of fixed wing pilots is going down dramatically in the last 20 to 30 years, but the population of helicopter pilots has been staying pretty much consistent. Unfortunately, the population of commercial helicopter pilots has been consistent at about 8,000 in the entire country, which is not nearly enough to populate the existing helicopter operations and UAM. So we felt that it was important to do something like the military did in the F-35 and simplify the vertical control system significantly, but we could leverage that existing population of commercial fixed wing pilots. So that takes care of the first stepping stone. The next stepping stone is because the population of existing or fixed wing pilots is going down dramatically. And one of the things that we concluded is the reason for that is the strong training burden that's required to become a pilot at the commercial level. So in order to keep the pipeline active for fixed wing pilots, especially since the airlines are likely to be able to pay significantly more because they can amortize the pilot's salary over 100 passengers per flight, as opposed to the UAM industry, which amortized the pilot's salary over maybe 2 or 3 passengers per flight. We felt that we needed to do something for the SVO2 operator, which aims straight at reducing the pilot training burden. So that's why SVO2 abandons the fixed wing pilot concept and goes completely new. So the completely new is not really completely new. One of the things we decided to do is to make it intuitive, the control system be intuitive. Intuitive basically isn't what the human brain naturally thinks. Intuitive really is what the human brain is used to doing. So one of the things that we know is that many of the potential pilots are very familiar with operating surface vehicles like cars, boats, motorcycles, bicycles, whatever. So SVO2 has control systems that's very similar to a car. Like for instance, if you want to turn in a car, you move the steering wheel and you hold it there as long as you're changing the direction of the flight path, the drive path, whatever you want to call it. So SVO2 has the same concept. You move the inceptor and you hold it displaced from center as long as you want to be turning, as opposed to the airplane where you move the inceptor as long as you want to be changing the bank angle. So that's why the change from SVO1 and 2. It's to deal basically with the pilot demographics and the expected need for pilots in the various operations.
Is the SVO2 Easy Fly? It looks pretty similar to how I fly my hobby drone. Same kind of controls.
It is very similar to that, and it's intentionally made that way because there are a lot of there are a lot of people that we expect will be interested in flying full-sized aircraft who may have experience flying hobby drones and with cars. And what you'll find is that when you get kind of a mix of hobby drone and cars, you end up with Easy Fly VTOL, where in the vertical space, it works a lot like a hobby drone, and the going fast space, it works a lot like a car.
I'll ask my one last question before I hand it over to the next guy. Are you suggesting that all SVO2 use Easy Fly? Or is it more like, well, this is what we think is the best path, but Part 23, Amendment 64 allows all kinds of innovation? Where do you stand on that?
Excellent question. And we didn't talk a lot about that, but that's an excellent question because it deserves a good answer. So the expectation is that any aircraft manufacturer can produce any kind of control system or display system or navigation system that they like. And in doing so, they will end up negotiating special conditions with the FAA, and they may end up negotiating pilot licensing and training requirements with the FAA as well. And they can do that however they want to do it. Our intent is to create a standardized path that OEMs can follow, because if you create your own path, it takes a lot of time and effort, and there's a lot of certification risk that your path may never be approved by the FAA. But if we can create a paved path that the FAA will recognize, that people can follow, then there is a definite certification certificate at the end of it, and they know how to get to that certification certificate. Our expectation is that many OEMs will follow that path because it is a defined way to get to their goal. And that's really what we're trying to do, is to create a path. Now, you also mentioned, is there only one way? And the Easy Fly VTOL, is that what we're proposing? Actually, that is what we are currently proposing. But as I guess about the third slide said, this is solidly set in sand. We have been working on this for quite a while. It's a concept that started at Langley in the 80s. It's been matured over the last 40 years. So there is some credibility to it. but it certainly does not have all of the details worked out. And that's part of why we are making these presentations to groups like this, so that we can get feedback and say, oh, you've forgot this thing. It's never going to work the way you proposed it. You need to do something different. Great. That's what we're looking for.
Who's next? Who else has questions? Thank you. Those are fantastic answers.
Rick Simmons, I got a question here. Are you going to do any research on the negative habit transfer of going from an SVO back to a standard aircraft?
Oh, that's a very interesting question. That's one of the things that we find when we've done these demonstrations, both the Bonanza and the Navion. We found that experienced pilots take longer to learn how to fly the aircraft precisely than people with no experience. So there's absolutely negative transfer. But the expectation is that, well, let me back up a little bit. The intent of these two paths, the SVO1 and SVO2, is not for existing helicopter and airplane pilots. It's for the demographic that we talked about. So SVO1 gives the nod to existing airplane pilots. So it behaves very much like an airplane when it's flying like an airplane, but it behaves very different from a helicopter when it's flying like a helicopter. SVO2 goes the next step and flies very differently for both modes. And we expect that there will be some negative transfer, but there's negative transfer also for those of you who are both airplane and helicopter drivers. You will note that there is negative transfer when you get a helicopter add-on or an airplane add-on, depending on which direction you go. So basically what that means is that you have to learn both sets of skills if you want to have a license for both aircraft. So that's definitely the case, is we expect there will be negative transfer. However, we also expect that the path from a conventional airplane or helicopter pilot to one of these SVO concepts will be significantly easier than if you started from scratch.
Okay.
Okay.
Excellent.
Yeah, hi, this is Craig Davenport. The question is related to the SVO2, SVO3 concepts and the level of certification and safety. Are you shifting the responsibility to, you're increasing the reliance on automation and other humans that aren't on board the aircraft and possibly the aircraft itself? Well, you are the aircraft itself. Are you just shifting workload now and responsibility, or are you expecting the level of certification of these aircraft and the supporting systems to increase to the safety assurance level?
Actually, what we expect is, as Borja mentioned, we have two different levels of reliability requirements. One is what we currently have today in Part 23 with AC 23-1309. But if you look at that advisory circular, and also Part 23 Amendment 64 mirrors that, but has a different classification for the aircraft types. But the Amendment 64 classifies the aircraft by how many passengers, non-crew members, passengers are on board the airplane. So basically what it says is that if there is only one passenger seat on the aircraft, then there is some reliability level. If there are up to 6 passenger seats on the aircraft, then it has to have a higher reliability level. If there are up to 10, then it has to have a higher reliability level yet. We have gone the next step and said that for the UAM world, we really aren't as interested, although we are interested in the number of occupants or potential occupants on the aircraft. We are also interested in the number of people on the ground who would likely be affected for the UAM world. So what we have done is we have taken the Category A requirements that Europe uses for commercial operations over urban areas for helicopters, and we have applied those to the SVO2 and SVO3 concepts to say that if an aircraft is designed to be operated over urban areas as a commercial operation, then it has to have a higher reliability, because it's likely that even though it might be a 2-place aircraft, that if it crashes, it may affect some people who are on the street below, or well, basically on the ground in the urban area. So that's part of the answer that I think you're seeking. The other part is, yes, we do intend to move the responsibility, especially in SVO3, from the pilot to systems, and in the case of SVO3, we consider the operation organization to be part of the system as well. And Borja briefly mentioned that for SVO3, because the intent of SVO3, which if you recall is the point and click control system, the person who is doing the pointing and clicking is not expected to have a pilot's license. If they don't have a pilot's license, it's not reasonable to expect them to be responsible for the safety of the operation. So somebody has to be responsible. And what we've concluded is that in the point and click environment, the only place it makes sense for the operational safety responsibility to reside is in an operational organization that has some sort of a safety structure. So that would be the Part 135 operator or the Part 121 operator, depending on the type of operation. So I don't know if that answers your question. It's kind of a long-winded answer, but that's kind of where we are in our thinking process.
I would only add that it's very critical for the OEMs to not be held liable for any more than what they should be held liable for, because that would kill the industry. You know, we got to.
Yeah, that brings up a very interesting point. And that, as I mentioned, back in the 80s, we did the bonanza at Beach Aircraft. So one of the things that I concluded as I was doing that bonanza is that we can eliminate many of the accidents that are caused by pilot error, especially the loss of control accidents. We could probably eliminate all of those. And so the Beach Aircraft during the 80s was sued a lot. And so I went to our legal team and I just said, so we're thinking about creating a flight control system that can eliminate pilot error accidents for, let's say, 9 out of 10 accidents. But at the same time, we will produce one accident out of that same rate that's clearly, no question, our fault, because we designed and built the control system. There was some fault in the control system. We can't do it perfectly. You legal guys that do all of our litigation, what would you recommend? And they said, no question at all. Go with safety, because when an aircraft crashes, independent of whether it's pilot error or not, we get sued. So it will be financially much better for us if the accident doesn't happen than even if a fewer number of accidents happen and they really are our fault than if pilot error accidents continue to happen. So I thought that was an interesting interesting answer, and it was very clear from their perspective.
No,
Okay.
Rory Feely, I'd like to dovetail on that. I mean, that's a very interesting perspective. Do you think something like SVO would force a change on some of those litigations? And I think about something like the Ford Explorer tipping over versus individual vehicle accidents and how those are currently litigated, because that's the mass transit system that we're looking at making a leap into the aviation space on. Do you see anything like these vehicles forcing a change on from the current environment on responsibility and liability?
Well, litigation is actually a political topic. It has to do with the laws that are passed by Congress. And so you're asking me to predict what Congress is going to do. I'm not going to wade into that. However,
yeah, why? Sorry, I never read that deeply into it. Well, I can predict what Congress is going to do. That'll be nothing.
well, that's kind of the case, mostly because historically, congressmen have been lawyers, and in the U.S. at least, there has been a strong tilt, in my opinion, towards litigation, especially compared to the rest of the world, Europe in particular. It's much easier to sue and win in the United States than, say, in Europe in an aviation accident. However, one of the things that I expect to happen is that accidents will significantly go down, because one of the things that we're really doing is we have found that, as Borja said several times in the slides, that the pilot error accident rate is significantly worse than the reliability accident or the reliability of most of the systems that are in general aviation aircraft today. However, when one of those systems fails, we always rely on the pilot to rescue the aircraft. And even when automation is not involved at all, the OEM gets dragged into court because of some sort of perceived design flaw or manufacturing flaw in the aircraft. So if we can prevent accidents, that's the biggest way to change the litigation landscape.
I had two additional questions for you. One, I think is a quick one. On your SVO1 proposal, or as I read it there, I understood you were using fixed-wing pilots, and I understand that you determined there was a shortage of commercial fixed-wing pilots. Do you not think it would be better to use both fixed-wing commercial pilots and rotary-wing commercial pilots for that SVO1 type certification?
Could be, but what we found is that the number of commercial helicopter pilots is, as I mentioned, 8,000 across the entire US, and that's been a pretty steady number for the last about 50 years. But it's not nearly enough to feed the UAM industry.
Yeah, no,
as
I agree. And then
pipeline patrols and oil exploration and EMS and those kinds of things.
yes, but at least that has a better regeneration rate than the commercial fixed-wing pilots, or if I understood it, or just the fixed-wing pilots in general, which seem to be on the decline, and the average age seems to be getting older.
Well, that's true, and you brought up an interesting point. Is that if you look at the demographics behind it, it appears that the acceleration, that the rate of decline of fixed-wing pilots is set to decline even more rapidly in the next 10 years, just because of the age of the number of fixed-wing pilots that is there.
And then I guess the next question is more of, I'm sorry, go ahead.
The other part for regeneration of helicopter pilots is that it's much more expensive and time consuming to become a helicopter pilot than an airplane pilot. And one of the things that we've noticed is that many, I'm not sure if most, but it might be most of the helicopter pilots get their training either through the military or as a VA benefit.
Mm-hmm. And so I guess, yeah, I agree. I think that's true. And then that training is generally of a pretty good standard. The other thing I would ask on just across simplified vehicle operations in general is, how do you see it progressing into like the critical phases of flight, for takeoff and landing, and particularly on aircraft that may have significant power margin limitations? Because ultimately, a lot of the OEMs are driving towards electrically powered aircraft, and with that comes excess battery weight. And if I think about SVO in the broader picture about what kind of technologies are required, it's probably a certainty that the kinds of sense and avoid and other technologies that will assist the pilot will probably add more weight to the aircraft in order to reduce what the pilot would normally do in today's standards from functions on board in terms of operating. Just how do you see that playing out as you see certifying those aircraft in those, the phases of flight that a lot of people regard as the most dangerous, and that's why we have, skilled and trained people in the cockpit, so to speak.
Yeah, excellent question. And we kind of glossed over that. There's a lot of things that were glossed over in the presentation, but that's one that deserves a little bit extra talking about. And that is in SVO2, if you noticed, and you probably didn't because we went by very fast, is all takeoffs and landings for SVO2 aircraft are intended to be automated, completely automated. Except that what we've also said is we've retained the idea that the pilot on board, because SVO2 aircraft will have a pilot with a pilot license, the pilot will authorize the initiation of the takeoff and will authorize the actual touchdown. But other than that, the takeoff and landing is fully automated, at least the way we've proposed it, set in sand so far. The SVO1 aircraft are still operated as today, with an airplane landing like an airplane, and the SVO1 aircraft landing like a V-35 aircraft lands today. So that's kind of the same. But we expect that just as today the OEM does not have to add an autopilot, Most of them do add autopilots to airplanes because of the value, the safety, and workload reduction. What we would hope would happen is that in SVO1, OEMs would start adding automated takeoff and landing in the same way that currently OEMs add autopilots. And you can see that that concept is just starting and taking its infancy already, and that the Garmin system has an emergency automatic landing system. It's not approved for normal operations, but at least the camel's nose is under the tent.
Thank you very much.
Nirmal, I think you had a question.
Yeah, thanks, Al. So I had a couple of questions. So the first one would be, I understand that SVO3 is completely autonomous, but with respect to SVO2 pilots, so how much of training will be required, for example, the aerospace and general flying discipline? So, I mean, I think a lot of time, yeah.
Yes, I like that one a lot. That's a great question. It's another one that we had to gloss over quickly, but SVO2 is one where we really expect the training burden to go down significantly. So one of the things that is a large training burden is all of the pre-flight stuff, which includes airspace, how much you have to stay away from clouds, depending on which airspace you're in, all those kinds of things. So in SVO2, we say that all flights in SVO2 aircraft will be IFR, under instrument flight rules. Basically, what that means is ATC will control the airspace you're in and control traffic separation, and will control cloud separation. So the implication of that is, if you are an IFR only pilot, you don't have to know airspace, which is really kind of an interesting concept. And that's one of the things that, for those of you who are experienced pilots, you will probably note that it's actually easier to fly IFR than it is to fly VFR, because you can just rely on ATC for lots of stuff. And so that's what we've done for SVO2 as well, is there's no such thing as a VFR only SVO2 pilot. All SVO2 pilots are by definition instrument rated, because they have to fly under instrument flight rules all the time. There's a lot of other things that we have included in SVO2 for pre-flight planning, like weight and balance, aircraft performance, things like that.
All right, well, I think now you just jumped to a huge change here, because up until this point, you know, when everything you've been talking about is basically about handling the airplane. Everything SVO2 or SVO1 is just keeping, you know, sunny side up, if you will. All right, but now you're saying, oh, by the way, this is not for recreational pilots to go out and get a hamburger. This is not for you to go out and do this or that. It is strictly ride the rails like an IFR type thing. So it's no longer a VFR is allowed on this. That's new territory, to have an airplane that's never allowed to fly VFR.
That's not quite true that you can't go get a hamburger, or you can't even go just look at your house from the air under instrument flight rules. In fact, those of us, well, this is a flight test organization, so you guys know that sometimes you do fly under an IFR flight plan, but you do lots of maneuvering that is very free form. The FAA ATC has a way to do IFR flying with block altitudes and maneuver in this area, let me know when you come back, those kinds of things. So the SVO2 pilot still controls the flight path of the aircraft, but they must remain within the confines of their ATC clearance, which could be a block altitude or a block of airspace, things like that. So it's not intended to be only fly the rails.
Okay. So would that be a different level of pilot then? Because instead of planning point A to point B, I'm going to go circle my house and go do whatever. So that requires a different level of pilot licensing to show that skill set for the people who would do that?
No, that's still an SVO2 pilot. The SVO2 aircraft, the pilot commands the flight path directly. Can also command the flight path through the flight plan, which would probably be more likely, which is actually why we concluded that, excuse me, thanks. So as we developed this SVO2 2 concept, the Easy Fly concept, we concluded, as one of the slides Borja said or showed, is that the control system affects the display, which affects the navigation. And we concluded that the SVO2 aircraft is primarily, not necessarily only, but primarily a transportation machine. So we tailored the control system and its environment around the transportation mission without restricting it so they can never do something else. But that's primarily what it is today, what we've defined it to be, where the airplane today isn't, it can be kind of most anything. It's not really defined to be anything in particular.
Al, that's part of our in-flight demonstration, where we have in an SVO2 aircraft implementation, like on the Navion, we have the ability to automatically couple to the flight plan and fly that all the way in. And or at any time, the pilot can basically move this stick. And because you are commanding flight path, we have a free-form segment where we do basically go look at a house, or we go over to the lake because it's interesting, or we change altitude or bank angle. But then we can come back and go back to the filed IFR flight plan, if you will. So we have different levels of autonomy depending on what they're trying to do, or augmentation.
Okay, that helps. Thank you. Okay, who else has a question?
Also, Al, I'd like to add to that is that as the slide earlier said, that our concepts are set solidly in sand. So if they need to be changed, that's why we are doing these kinds of presentations, so we can collect these kind of concerns, or where we have left a hole in our logic or things like that.
Oh, and by the way, I'm copying the chat, and I'm going to send that out to you guys. I know you're busy right now. You don't have a chance to answer it, but at least you get some of the comments from the chat.
Hey, Al, Raymond Schreiner here from Whiskey. Just wanted to know if we want to find out more about the SVO concept, is there a paper or some technical details that we can read into all the details?
Well, the paper itself, the most recent one, is already posted on our corner of the website. But I'm sure Noel and Borja can tell you where more information is.
Yes,
Whisk is a part of
like,
GAMA.
we've got our email here at the bottom of the slide. If you wouldn't mind reaching out to us via email, Noel and I are happy to respond.
Well, I was also going to say, Whisk, you're a part of GAMA, is that right?
Yeah, we participate in a lot of the working groups.
Okay, so if you're a member of GAMA, we have a kind of a special relationship with GAMA, because they represent lots of companies like yours that can give us a lot of feedback about how we should change what we're proposing. And because of that, we have provided GAMA with the report as it is progressing along, and GAMA can provide you a copy of the report as it stood at our last update, and we can continue to update that report through GAMA.
And what do you call that report again?
Just call it the SVO report from Noel and Borja. They'll know what you're talking about.
Thanks.
We need a better
what
title.
The official name is. Yeah, we ought to come up with something classy. You think, Borja?
Yeah, I agree. But again, sorry, I don't know who just asked the question, but please reach out to us via email. We'd love to coordinate and love to get your opinion on some things.
Yeah, sure will. It was RJ Schreiner. I'm the chief test pilot with Whisk Aero.
Pleasure, RJ. Thanks for your questions and your time today.
Any more tomatoes?
Maybe we can spend the last couple of minutes watching that video.
Sure. Let's go back. Okay. So I guess for the record, since this is being recorded, this is a video that was produced as part of an FAA-sponsored research project by the Small Aircraft Directorate and I guess it's Policy and Innovation Division. Our chief technical point of contact was David Zizo, and And this basically shows what we do in flight, but we cut this video on the ground to be able to make the video editing processing easier. Here goes.
Do you want tea?
No, thank you.
At the time, the control technology and hardware was too expensive to be affordable to the community that needed it the most. Personal general aviation. Recent advances in non-aviation consumer technology has made the hardware and software needed to implement these augmented flight path control concepts affordable and accessible enough that they can be implemented safely and at a cost that is affordable for general aviation. These concepts are also a key enabler along the path towards transformational flight vehicles for an urban air mobility industry, where pilot workload is envisioned to be methodically reduced to the point of just having passengers riding along in a future air taxi system. This research project allows us to get real-world experience with pilots flying the technology, which leads to identification of safety requirements and methods of compliance that can be applied when these types of controls are proposed for certification by applicants with new vehicle concepts.
Let's start with a tour of the cockpit. This aircraft is a flight controls testbed for general aviation aircraft. The left seat is used by the evaluation pilot and the right seat is used by the safety pilot. The right side of the cockpit has standard controls and displays for safety purposes. The top display indicates whether the evaluation system is engaged or not. When it's not engaged, it says easy fly off. When it is engaged, it shows where you're going from the pilot's point of view, even if there are clouds obscuring the view. This display shows the flight path marker. This is where you are going. Obstacles, runways, and other items of interest to the pilots. Bottom display shows a moving map. Both displays are touchscreen. There is also a center stick. The position of the center stick relative to the spring center location commands vertical flight path angle and turn rates. This type of control system is called a velocity vector command system, since the position of the stick directly commands the direction of the velocity vector. With this system, you move the stick to directly command the aircraft's direction of flight. In a conventional airplane, moving the stick commands a control surface position, which changes the aircraft's attitude, which in turn changes the direction of flight. Fore and aft motion of the stick commands vertical flight path angle, resulting in the airplane climbing, or descending. Returning the stick to the center position will result in the aircraft holding its current altitude. For long climbs and descents, push and release the lock button, which is the black button on the side of the stick. The stick will remain in this position. To unlock the stick, press the button again, or overpower the lock and move the stick from the lock position. Left, and right motion of the stick commands turn rate. Centering the stick will result in aircraft holding its current course. A maximum of 45 degrees of bank is allowed at high speeds. Maximum bank angle is reduced as speed is reduced to prevent accelerated stalls. The flight path marker is placed on a point and the aircraft will fly to that point. The position of the speed command controller commands airspeed. The minimum commandable speed is landing approach speed, and the maximum commandable speed is the aircraft's limit minus 10 knots. This is the basic manual operation of the system. There is no way to override this and directly control the elevator, ailerons, or rudder surface, or the throttle valve like a conventional airplane. The system has many built-in protections. These include angle attack limiting to prevent stalls, G-loading, bank, pitch, overspeed, ground collision protection, and automatic level flight. To demonstrate some of these protections, we will start from level flight and hold the stick full aft and full left. The aircraft starts a climbing left turn with an initial bank angle of 45 degrees. As the aircraft climbs, the power goes to full and the airplane slows. As the airplane slows, the bank angle is reduced. The airplane continues to slow until it reaches its maximum climb angle of attack. The maximum angle of attack allowed corresponds to the maximum climb speed. Note that this is slower than the minimum commandable speed. The only way to get the maximum angle of attack is climbing at full power. Moving the stick full forward and full right causes the airplane to descend in a right turn. As the speed increases, the bank angle increases to match. As the speed increases past the commanded airspeed, the power goes to idle. As the airspeed nears the maximum allowed, the airplane pitches up to limit the speed. This entire maneuver happens